All right. Thank you very much. My name is Aaron Rossetto, and I'm here to tell you a little bit about some of the work that I've been doing at Cirrus Logic regarding DXE driver validation for our smart amplifier and codec silicon that goes into consumer PCs. I worked at National Instruments, which was recently acquired by Emerson, for 22 years, doing drivers and firmware for high-speed data acquisition and software-defined radio devices. And about 3 years ago, I moved over to to Cirrus Logic to work on PC audio silicon. The great thing is that audio is a lot like data acquisition, just 2 to 3 orders of magnitude slower. So I'll tell you a little bit about the motivation for the work that I did, workflow that I came up with, and the solution, an overview of the solution, and some results and conclusions, and something of a call to action to you guys, maybe a little bit of a plea, if you will. This story actually begins on the very first day that I started at Cirrus. And as I'm sure most of you know, starting a new job is a little bit like drinking from the fire hose. And that's exactly how I felt on that first day when I sat down in my manager's office, really nice guy, and tried to get a lay of the land. So as I said, Cirrus Logic creates silicon for PC audio, smart amplifiers that have DSPs in them that sweeten the audio, are able to drive the speakers as hard as they can go to get the loudest, best sound and have feedback loops to make sure that the speakers don't blow or explode. Codecs that have MCUs in them so that they can perform capture and render, jack detection, that sort of thing. And this was a relatively new business area for Cirrus. Cirrus had been well known in the mobile space for audio, but now we were trying to enter the PC audio space. And that meant a whole bunch of different requirements coming from our new customers. And what my boss had said was, well, we got these customers who want to do firmware and configuration download, what we call tunings, basically all of the knobs that we can twist on the DSP algorithms to make the audio sound really good. But they want to be able to do that from a secure environment. And this is literally a quote from my boss. They're asking us about DXE drivers. And I thought that was kind of a strange thing. I knew very little about UEFI at the time. And essentially, it was my job to go and figure that out. All right, so I got to work. And this is what I had to work with. This is a picture here of our development system. At the very top is a little NUC-like PC. It's got an Intel SoC on it, and one of those 40-pin hat connectors, like you might see on a Raspberry Pi, where a lot of those signals from the SoC can be routed to a board that you design and attach, which is what we did. And on that board, this particular one has 8 smart amplifiers, 4 speakers, connected to them. The other 4 amplifiers were not used, and a codec, and you can kind of see at the bottom these ribbon digital mics connected to it. And this is what I had to work with, so I thought my first step was going to be, okay, let me see if I can at least talk to the silicon from this strange UEFI environment. And so I did all the research that you'd expect somebody new to UEFI to do. I downloaded EDK2, I built things, I downloaded the spec, I downloaded several specs looking for all the information that I needed, and I got to the point where I knew what my approach was going to be. So I'd read about this I2C master protocol. These chips have both I2C and MIPI SoundWire interfaces, and given that it looked like there was I2C support in this strange UEFI thing, I figured I'd use that. Except on this particular device that we were using, its stock BIOS did not have the I2C master protocol. So that sounded like a challenge. And I ended up writing basically my own I2C driver based on some of the older code that I had seen on the EDK2 platforms repo. That I2C IP that's in, I think, a long generation of Intel SoCs is all based on the same designware IP that they've been using for generations and generations. Doesn't really change. It's got a relatively simple register interface. And there was what looked like the shell of a driver that implemented a lot of the I2C master protocol API. So put that together in my own driver, built it, created a little application that looked for that protocol, initialized the protocol, and then did an I2C transaction to read the device ID register on one of these smart amps. And believe it or not, within about 2 weeks, I had that working, and you can see that screenshot there. The read result was an I2C read transaction of the device ID register, which is 35A56. So I'm pretty excited at this point. I figure, okay, got a big raise coming. My boss is going to be really proud of me. Not too bad for the first 2 weeks on the job. So from that point on, I figured the rest of this was going to be relatively straightforward. So I got to the point where I had written a DXE driver that I could load manually from the UEFI Shell that implemented that I2C master protocol. And then I wrote another firmware update driver that would connect to the I2C master protocol. It would read the hardware configuration, like the I2C address, which PCI I2C controller it was connected to from a big binary EFI variable that I had crafted. It would get the firmware files off of the EFI system volume because I'd copied them from a USB stick onto this piece of the drive. And then it would program the firmware via the I2C driver. And I actually got that working, and this is great. Went to show it to my boss, and he said, "Good job, Aaron. You've done very well. Now, how is this going to work on a customer system?" And I kind of looked at him like this because I had absolutely no idea. You guys are probably laughing, not just because it's a funny picture, but you're thinking, wait a minute, firmware doesn't get loaded from the EFI system partition. It doesn't make sense really to store it there. Configuration data may be in an EFI variable, but that doesn't really make sense. Typically, it would come from platform configuration data, right? This is all things that I kind of learned later on in this process. Well, this workflow was really great for manual testing, but clearly it's not representative of what it would look like on a customer system. We are not going to ask customers, oh, okay, if you buy one of these laptops, please boot up to the UEFI Shell and run these commands, and then you may boot into Windows and get your high-quality audio experience. The problem, though, was that for this particular platform, and so many other platforms, building a custom BIOS is just not an option. We don't have the proprietary bits that only the IBVs get. A lot of stuff is very locked down, signed, and I understand why. Don't get me wrong, I understand why this needs to be the case, but that really did present a pretty big impediment to the work that I wanted to do and to show off. And my boss kept telling me, well, we're the integrator. The customers who buy our silicon and integrate it into their SKUs are going to look to us for information on how to integrate all of this stuff onto their platforms. And at this point, despite the success I had no idea how to tell an ODM what to do with all this collateral that we'd come up with so that it would actually work on a customer system. I just didn't have that knowledge. So what do? Well, I go back and start doing some more research. And in the process of doing this research, I found OVMF, the Open Virtual Machine Framework, which is an EDK2-based project that enables UEFI support that can run in a virtual machine like QEMU. And that kind of gave me an idea. Well, if I can build a virtualized, or a BIOS that would run in a virtualized machine, that's got to be a really good way to learn about how it should work on a real machine. And it was. That was basically the way that I learned how a DXE driver binary got integrated into the firmware volume, as well as the collateral that the smart amps needed, like their firmware and their tunings, and how to use platform configuration data to specify all of the stuff that the firmware driver would need in order to do its job. But there's still one big gap here, and that is I can do all this wonderful stuff, but it's essentially useless unless I can talk to the silicon and take all this stuff and put it where it needs to go. Again, more research. And I kept seeing a lot of references with OVMF and QEMU to PCI pass-through. And typically all these references that I'd read were related to passing through GPUs to the guest, so that somebody could run Linux as a host, but then have Windows in a virtual machine and give that virtual machine full access to the GPU, typically for gaming purposes, right? And that gave me an idea. Well, the I2C controllers that my driver talks to are PCI devices. Maybe I could use PCI pass-through to hoist those controllers up into QEMU and make them accessible to my custom BIOS. So to do that, on that little NUC that we use for development, I installed just some version of Ubuntu because it's relatively easy to get set up and ubiquitous. I had QEMU running a OVMF build that I'd created just by cloning the repo and following the instructions, which are very good, by the way, and then enabling PCI pass-through of the I2C controllers in the kernel options for the Linux host. In order for this to work, in order to take a PCI device and pass it through to a guest, it requires that all PCI devices that are in the same IOMMU group all need to be passed up through to the VM. And on the Linux host, I could run the lspci command, and I could see the IOMMU group assignments for the PCI devices. And in my case, it's that first one there, bus 0, device 19, function 0 was the I2C controller that I wanted to talk to because that was the one that was pinned out to all of the silicon. However, because there was this other I2C controller device in the same IOMMU group, I would need to pass that one through as well, even if I were not using it. So by modifying the kernel options on the Linux host and rebuilding grub and all the things that you need to do to enable that, you could see here that I wanted to assign those two I2C controllers that are in that same IOMMU group to the VFIO PCI driver, so that rather than the normal kernel I2C driver that Linux would bind to these devices, it would bind to the virtual function driver instead. And I think that last parameter there, that disable idle D3 on, I remember having to put in because I think what was happening is when the device was idle and going into D3, I was no longer able to access it from the guest. So I think what that did, if I remember correctly, and this was a while ago, was to prevent those I2C controllers from being put in that low power state by the Linux host so that they would always be visible and accessible within the VM. So making these changes and rebooting the system into Linux, I could see that now the kernel driver bound to these I2C devices was the VFIO driver. So we're definitely making good progress here. And then once I had done that, I started QEMU and specified this additional VFIO PCI-based device, the I2C controller that I wanted to have in the virtual machine. I had to specify its PCI address, its bus device and function number. And then also the custom BIOS that I had built, where I was learning how to integrate the DXE driver and the firmware and tunings into the firmware volume and all the other things I needed to do to make this look like a real system, specify those options, and then start the virtual machine. And once I had done all of this and booted to the UEFI shell and typed the PCI command, I confirmed that now that PCI I2C controller with vendor ID 8086, device A0C5, that's the one I wanted to talk to, was now visible from the VM. Except it had a different PCI address. It was addressed, which is fine. It just meant that I had to go and change the configuration data for my driver to say, instead of the expected 0190 address of the I2C controller, in this case, because we're on a virtualized platform, we had to use that address instead. Now with this, I was able to test it out by loading my I2C, simple I2C driver that implemented the I2C master protocol. I could have integrated that into the image, but at this point it was still very early on in my research. And then running the DH command, looking for handles that had my I2C master protocol, confirmed that it was there, and attached to that PCI device with the new address, 020. And then I could run my diagnostic tools again in the VM and read the device identification register of the smart amp, confirm that I was getting the right value, which meant that the communication with the hardware was successful from the virtualized environment. So this was a really great alternative because for us, building a custom BIOS was just simply not an option. There were some other sort of benefits that came along with this too. The primary one being the fact that QEMU has this monitor mode to allow the state of the VM to be examined without having an external debugger. And through that, you can have QEMU print out all of the PCI register read and write accesses that it was doing to the device, which helped quite a bit during the debugging phase. Note that I could have done the same thing by logging all the register reads and writes that I'd done in my own driver, but that would have cluttered up the driver, cluttered up the logs. This was just sort of a nice sideband way to determine if my driver was operating correctly, which I had a pretty good sense that it was, given that the register accesses on these pieces of silicon was working as expected. But, you know, as we tried to bump up the speed, the I2C speed, and maybe things didn't work, it was a good diagnostic tool. And that can be enabled on the command line when starting QEMU with this monitor option, and then enabling traces of all the VFIO accesses. This also gave me another idea because I had mentioned earlier that the silicon that we have connects to the host over I2C and or this MIPI SoundWire interface. And at the time, I don't believe there was a SoundWire driver that could run in the UEFI environment, and be really nice if we could not need to have both interfaces connected to save the pins, save the routing on the board, etc. And I kind of got this idea in my head that, well, through this, I could see how, for instance, the Linux kernel, if I ran Linux as a guest in my VM, would talk to the Intel ACE, that's their audio communication engine or whatever they call it, which is how they control the SoundWire bus. And maybe I could create kind of my own bootleg SoundWire Dixie driver by studying that along with the Linux kernel source, and correlate the register writes that were being logged with the operations that I was reading in the Linux kernel source. Unfortunately, that came to a dead end because the Linux kernel needs a lot of information in ACPI related to the SoundWire controller in order to fully initialize. Otherwise, if it doesn't find it, it fails. So I took all the stuff from the DSDT related to the SoundWire and built a custom set of DSDT and ACPI tables from my virtualized platform and tried to load them with the ACPI table option, and it failed. It appears, at least maybe I was doing something wrong, but it appeared at the time that there is a 64 kilobyte limit on the size of the custom DSDT that you could provide to the guest. So that was problematic. So in conclusion, this is a super powerful technique, and it worked really well, and it gave me the knowledge and the confidence to go and then tell the ODMs, okay, here's what you need to do to the BIOS for this platform in order to incorporate our driver and our collateral, and have a pretty good chance that it was going to work. But that said, nothing beats real hardware, right? That's where the rubber meets the silicon. The rubber meets the silicon. And when I was pitching the idea of coming to give this presentation at this conference to my boss, I told him that given all of the trouble that we have had in finding platforms where it is relatively easy to build a custom BIOS for real hardware, I pitched this as maybe somebody out here would have some alternatives for this kind of problem. And when you guys probably don't have really any problems with this. You have all the proprietary knowledge and bits in order to build BIOSes for these platforms, whereas, we're just a little guy just doing our little quaint drivers here. So my call to action would be, if it is at all possible, to have either some sort of list or a list of sanctioned platforms with good instructions on how we could do something like I ended up having to do in a virtual machine, but on real hardware, so that we could get that experience and that knowledge that we needed to make our product a success. I believe that if I did some research, and I think I had a colleague spend 3 or 4 weeks trying to build a custom BIOS for an Intel RVP that we had in-house, but a lot of the bits that we found that were available were for much, much older versions of the Intel SoC. Think KB Lake or something that's basically ancient at this point, when at the time we were trying to use Tiger Lake, now also pretty ancient. And it's going to be much more difficult as we move into trying to do this sort of thing for future Intel SKUs or other SoC manufacturer SKUs. And so with that, that's all I have, and I welcome your questions. Thank you. Yes, please don't make it too hard of a question. I'm still a newbie.
Oh, no, I'm not intimidating at all. Don't worry. Inside joke. But actually, I was just going to say yesterday we were just discussing how bad the wiki was for the EDK2 on getting started. And just wondering if, not right now, but just on the mailing list on the EDK2, if you could give us some feedback on what would have been, what was broken, or if it could have been better, because we're looking into improving it, and also maybe to ask at some point to maybe get you to add some information to the wiki about how to do a recipe for doing the pass-through, because I think other people could find that really useful.
Yeah, I think that's a great idea. Personally speaking, thinking back to when I started, I don't recall the EDK2 setup to be particularly difficult in the getting started. I was building it within 10 or 15 minutes of cloning the repo on my system, but that I know that's definitely a problem, and certainly a lot of this PCI pass-through and the use of OVMF with that information was cobbled together from a number of different sources, and having it all co-located in one spot that's easy to find would be a really good idea. So I will take that to heart.
Well, thank you.
All right. Thanks once again.